This is Neil Patwari, and this video segment is going to explain why the Nyquist filtering theorem is a craft activity. I'm going to talk about the Nyquist filtering theorem, but I'm going to talk about getting a pulse shape in general that is orthogonal to the n times t sub s delayed version of itself for every integer n. That is that this set of functions, p of t minus integer n times the symbol period, for every integer n, form an orthonormal basis. And this is so that each symbol can be perfectly separated from other symbols sent during other symbol periods. In other words, we don't want the bits we send during one symbol period to interfere with what the receiver is going to receive during the next symbol period. We want those two to be perfectly separable. To figure this out, we're going to define the autocorrelation function Rp of tau of the pulse shape P of t. Recall that when I have tau equal to 0, this is the energy, and that energy should be 1. So I have Rp of tau should be 1 at tau equals 0, but it should be 0 at all other multiples of t sub s. So we could just use this information and we could try to find different pulse shapes that would meet this criteria. But the Nyquist filtering theorem gives us an easy way to come up with lots and lots of different pulse shapes that meet that criterion. The Nyquist filtering theorem says that a necessary and sufficient criterion for this condition that we need, that Rp of tau is equal to 1 at tau equals 0, and 0 at every other integer multiple of tau, is that its Fourier transform satisfies this condition, that the sum of copy and pasted different versions of Rp of f, copy and pasted at every integer multiple of 1 over t sub s, that sum is equal to a constant of t sub s. And we're not going to go into the proof of this, although it is in Appendix A of the Rice book, and you should read it and convince yourself. Basically, Rp, it doesn't matter what it is, as long as when we copy and paste it together at different integer multiples of 1 over t sub s, that it adds up to a constant. How do we get that? One way is to set Rp of f to the rect function. That is, that it's completely constant, equal to the constant that we need, t sub s, between negative 1 over 2 t sub s and positive 1 over 2 t sub s, this window size of t sub s. What does that look like? So I draw a rectangular function between minus 2 t sub s and plus 2 t sub s, and then I copy and paste it and put it next to there. That is an offset of 1 t sub s. Copy and paste it and put it again next to that. It's an offset of 2 over t sub s, and I put 1 before. You can see this would go on to infinity, and if I had lined up these exactly right and drawn it perfectly well, then you would see that it's exactly a constant when I add it together. In fact, this value here would be t sub s for all frequency, and that's what the Nyquist filtering theorem requires. So that's one example. The problem with this example is that these very sharp transitions in the frequency domain then have major ripple effects in the time domain. That is, they cause big ripples, large slope in the time domain. And although it meets the criteria, if my receiver is off in time, in sampling time, and it doesn't get to exactly t sub s to its sampling time, well, the results are going to be poor. So we don't like to have frequency spectrum with sharp edges. But we don't have to have sharp edges because we can do something else. We've got another example. And this is basically that the edges of RP of f don't need to be 0. That is, it can kind of bleed into these next frequency windows here. It doesn't have to just be non-zero between minus t sub s and 1 over 2 t sub s. An example would be this. I've taken this rounded RP of f in the frequency domain, and I've copied and pasted it every integer multiple of 1 over t sub s. And you can see that it isn't limited to minus 2 over t sub s. In fact, it is non-zero everywhere here between minus 1 over t sub s to plus 1 over t sub s. But when I copy and paste it and I add it together and I add this value and this value, I get a constant. I get back up to t sub s. So as I add this together, I get this same constant because whatever is missing from the t sub s is copied in the value that is overhanging the edge of the t sub s, that first t sub s, 1 over t sub s wide window. Okay, so they add together to be t sub s. That's a short story. And this one I tried to draw as a cosine shape. The cosine has this, slowly increasing slope, then slowly decreasing slope, and it's symmetric in this way that adds together. So a raised cosine, because it is not below 0, it is all above 0, and it's multiplied by t sub s. So this raised cosine RP of f will lead us to a pulse shape that is called the root raised cosine pulse shape. And you and I can come up with our own RP of f. It doesn't need to be a cosine, it just needs to be symmetric in this way, about this point, 1 over 2 t sub s in the frequency domain, and it's symmetric about t sub s over 2 in the vertical axis. It has this double symmetry that we need to have. And I'll show you how to do this in this craft activity. Okay, I'm going to tell you how to make your own Nyquist filter out of a sheet of paper, some scissors, some paper clips, a pen, and we'll start by taking the 8.5 by 11 sheet of paper, and we're going to fold it on the long side. And I'm going to try to make sure it's lined up while I'm doing this, so that I get the edges lined up with the edges. And I'm going to then take it and I'm going to fold it again on the other side. And I'm going to unfold it and I'm going to write my axis. So I'm going to have the horizontal part is going to be the frequency axis. This is going to be the amplitude of the pulse in the frequency domain. So on my vertical line, that's going to be halfway through our frequency range. That is 1 over 2 t sub s. So I'm going to draw this line right on the folded edge, and I'm going to label that as 1 over 2 t sub s. Okay, and then I'm going to draw the horizontal line. I know that my pulse shape has to go up to a constant of t sub s. So I'm going to label this line with t sub s divided by 2 because it's halfway up to the top. The top line will be t sub s, halfway will be t sub s over 2, the bottom will be 0. Okay, and so now I'm going to fold it up again, just as I had a second ago, and I'm going to take the double folded edge in one hand, and the edge that doesn't have any folding at all, that's the other corner. What I need to do is I need to have a pulse shape that starts approximately here. I'm going to cut it slightly above this corner so that I don't completely tear my sheet of paper apart. But that's kind of arbitrary, as I'll show you. So I'm going to cut here I'm going to cut here, and I'm going to do whatever shape I want in the middle here, but I have to get up to t sub s over 2 by the end of my frequency axis. Okay, so I'm going to take my scissors. Okay, some of it falls out. And in fact, I didn't do a great job of cutting it, so it's not going to be connected in the middle very well, but it is slightly connected there. So what I'm going to do is I'm going to paper clip it to another sheet of paper so I can show you. Okay, so what's going on here is that I have my pulse shape between frequency 0 to 1 over 2 t sub s here in the middle, and then t sub s 1 over t sub s on the end. So this halfway point, my signal crosses through t sub s over 2. And just to be more explicit, I'm going to draw what that function is. It follows the edge of one of the halves of my sheet of paper, and then comes down and reaches 0 by the time I get to a frequency of t sub s over 2. So you can see that I have this function that is drawn on the f-axis that represents this function, but I can also see it as the edge of my sheet of paper. And the time-shifted version is the other section. It's this one that starts over here and comes up over here and is up and is maximum at 1 over t sub s. Okay, and so you can imagine this repeated over and over again in each integer multiple of 1 over t sub s. That gives you a filter that meets the Nyquist sampling theorem, or sorry, the Nyquist filtering theorem, because it does provide this shape that the bottom part that you're taking away, that is this part over here, is the same as the one that you're adding in over here. Okay, so that's why it meets the Nyquist filtering theorem. I think it helps to look at the symmetry as what you would get from your average snowflake cutting exercise that you've probably done 100 million times before. So that's how easy it is.